Hello, hi everyone. So today I will be presenting the paper titled Aircraft Recognition Using Convolutional Neural Network. I am presenting this paper on behalf of Nabila, Junhuang, as well as Grace. Before we get into the main body of the presentation, let's go through the items that we are covering today. We'll first start off with an introduction about what the problem as well as the objectives of the research going to be, as well as the literature review and the methodology in which the research was conducted based on. And then it will be followed by the results as well as the discussions. And we will then proceed to the conclusions and we'll finish off with the future work recommendations that can be done to enhance the contribution to this particular area. So now without further ado, let's get started with the problem statement. So we know the process of recognizing aircraft in satellite images is an important task for both military and commercial applications, whereby the detecting system must be equipped with detectors that are able to separate the aircraft from background that may look very similar to the aircraft itself, and the process itself can be very tedious. So it presents itself as a gap and a problem that is to be solved. And this serves as the motivation behind the study. So the objectives of the research can be summarized in three main points. So number one, we set off to design an aircraft recognition system that is able to recognize aircraft and determine the quantity, as well as be able to quantify the accuracy of this particular detector. So now, based on the literature review, the wider research community has been employing different methods in order to develop aircraft detection systems. These methods include support vector machine, deep neural network, as well as convolutional neural network. These methods have been able to achieve detection rate in the range of 85 to 99%. So now the research gap and question that may be asked is how about region-based convolutional neural network that is able to sample and count multiple aircrafts present in one single image. So that's what we set off to achieve over here. All right, so now on to the methodology. So we know that in order to train the RCNN model, we need images with multiple aircrafts in it. And in order to train the model to convergence, we need a high number of data set. So in order to achieve that, we went to Google Maps and particularly airports all around the world with aircrafts lying around. And we use the snipping tool to sample the satellite images that contain multiple aircrafts. So one example that's being shown here is we can see that there are three aircrafts in it. After we have gathered the dataset that we need, we split it into training and test dataset at a ratio of 7 to 3. Then after that, we will proceed with the pre-processing of the data that we have just gathered. This includes resizing, introduction of noise, as well as performance of physical transformation of the images itself. So this includes mirroring as well as turning it upside down. In terms of the actual flow of the methodology, it has been summarized on the right-hand side in the flowchart. So again, first started with the collection of training dataset, as mentioned before, and we'll crop the region of interest out to ensure that at least it contains one aircraft and it's not limited to just one. Then we will perform the design of the architecture and the fine-tuning of the hyperparameter before we will train the fine-tuned neural network with the dataset that we have just gathered. Then we will check the mini batch accuracy. Then we'll test the accuracy of the newly developed system. So in order to crop the region of interest, we will actually use built-in toolbox on MATLAB using the image labeler, whereby we will be drawing boxes around the images as shown over here. Again, we have three aircrafts that will draw three bounding boxes around it. So now on to the codes to train the input dataset. So again, all the implementation was being done on MATLAB using the built-in neural network ML toolbox. Some of the code snippets can be seen over here. I'm not going into the details. Okay, so now on to the section of the code that will be used to produce the results. So what we're trying to do here is really to use the newly trained model to predict based on an input image. So a sample over here is where we supply a sample image with two aircrafts. So you can see there's one big and one smaller aircraft. The model is able to accurately detect the aircraft and also draw the bounding boxes around the region. So we need to say the model is not only able to detect two aircrafts in this particular image, is able to know where these two aircrafts are being located. All right, so now moving on to the results and discussion. So we have separated the results into five main sections, whereby for each cases we increase the number of aircraft in the image and we evaluate how well the model performs. So for the first case, we only have one aircraft. The model is able to detect it 94% of the time and able to draw the bounding box around it. Well, 6% of the time it's not able to detect anything. And when we move on to two aircrafts, the ability to detect both aircrafts or all aircrafts in the image, it should drop to 81%. And 60% of the time is only able to detect one, and versus 3% of the time it's not able to detect anything at all. And further, when we increase it to three, we saw the accuracy of detecting all three aircraft drop to 48%, whereas 48% of the time is able to detect at least one, compared to 4% of the time it couldn't detect anything at all. And again, this number is again a further change where we move on to 4, whereby the ability to detect all aircraft dropped to 32, whereas 64% is able to detect at least one, whereas 4% of the time none will be detected. And lastly, the worst case, like the most complicated case, where we have 5 aircrafts, the accuracy of detecting all 5 aircrafts dropped to 27%, whereas 44% of the time is able to detect one or two, 29% of the time is able to detect 3 or 4. And surprisingly, when we have 5 or more aircrafts, the model was able to detect at least one aircraft. So that's the reason why we have a 0% in terms of occurrence, whereby no aircraft was being detected. Now moving on to the precision and recall analysis. So based on we just again we separated into two different ways to quantify the results. So first row, as you can see, will be based on the total number of images, and secondly will be based on total aircrafts. So again, because each image may contain more than one aircraft, so that's the reason why we separated out based on images and aircrafts. So for the case of the images, we can see that the precision is at 58.45% and the recall is at 94.24%. And for the case where we consider the total number of aircrafts, this number of both the precision increased to 89.29%, whereas the recall actually dropped to 76.3%. So in conclusion, this model is able to recognize aircrafts from satellite images, and whereby the image may contain more than one aircraft. And this model is also able to draw the bounding boxes around the region that may contain the aircraft. So it's able to localize where the aircraft is being located. And the final performance of the model is at 58.45% for precision and 94.24% for recall. Now, in terms of future work recommendations, of course, the immediate next step will be to increase the size of the data set and to perform further optimization of the CNN layers, as well as experimenting with some of the newer architecture that may be available to the research community. Whereas if time is concerned in terms of training and running of the model itself, faster RCNN should be the architecture that should be explored and to be evaluated how well this will perform against the current RCNN implementation of this particular detector. So with that out of the way, that will be the end of the presentation. Now we'll open the floor to any potential questions. Thank you.